Welcome to page 3. Again, we're just doing more examples using Green's theorem. So example 2, use Green's theorem to evaluate the line integral along the given positively oriented curve. All right, and so because we know that we have a region. All right, so here we have the ellipse x squared plus 2y squared. So we know it's a simple closed region. And it says a positively oriented curve, so which direction that we're going. So we know that, okay, now we can apply Green's theorem. And so over here, if you want to know what the ellipse looks like, it's x squared over 2 plus y squared equals 1. And so going ahead, just applying Green's theorem. We want to go ahead and just, not have to do this directly, just use Green's theorem. So we're going to take the partial. So the partial of q with respect to x, the partial of p with respect to y. So we're taking those partial derivatives. When we do so, the partial derivative of 2xy cubed is just going to give us 2y cubed. The partial derivative of y to the fourth is, with respect to y, is just 4y cubed. So now let's go ahead and take the difference of those two, which is going to be negative 2y cubed. And we can go ahead and say that that's 0. So if you don't see this, and again, I'll explain why that's the case. If you don't see this, then you can go ahead and break this up into the integral, and we can say, we'll use x's on the outside. So x is going to be the square root, negative square root of 2 to positive square root of 2. The integral for y is going to be negative 1 to positive 1. And along, we have our, so I'll put negative 2 on the outside, y cubed, and then because I have y on the inside, dy dx, I could break it up and then I could work with it that way. But again, if you already know that, because we're dealing with y cubed as our function, and it's an odd function with respect to y, and d is symmetric about the x-axis, then we know that when we're plugging in our values, we're going to be getting 0. And so that's why I just went ahead and say that's 0. Again, you can use that information. If not, if you don't see that, then you'll just continue working along and then solving your double integral this way. All right. I don't know why I didn't keep that box up. All right. For example 3, use Green's theorem to evaluate. All right. So our line integral, again, that's the notation for line integral, the dot product of f and dr. Check the orientation of the curve before applying the theorem. Again, if you want to see the dot product, remember, if we have a vector field, f is going to be pi plus q j, and r is going to be our curve, and so it's going to be xi plus yj, and then dr would just be dxi plus dyj, and then here, if I take the dot product between the two, then the dot product is just going to be that integral over some region c p dx plus q dy. So again, that's just another, that expression there, which we've been really working with today, is just another representation of looking at the line integral. All right. I'm going to erase that because I don't want that just on the notes, because the less you see, the less confused you could get. All right. So we're going to use Green's theorem to evaluate our line integral. We want to check the orientation of the curve before applying the theorem. So here we have f, our function e to the negative x plus y squared, and e to the negative y plus x squared. So there's our vector field. All right. C consists of the arc of the curve y, which is equal to cosine of x from negative pi over 2 to 0, and then to pi over 2 to 0. in the line segment from pi over 2 to 0 to negative pi over 2, 0. So initially, all right, we're going in a clockwise manner, because if C consists of the arc y equals cosine of x from negative pi over 2 to positive pi over 2, we're moving along that top curve, and so again, that's clockwise. Same can be said for our line segment. We're starting at negative pi over 2 and headed to, it's positive pi over 2, headed to negative pi over 2. So again, we're going in this clockwise rotation. We don't want to be going in that orientation. So what we need to do is we need to counter that by saying, okay, negative C will put us in the positive direction. And so instead of, holding our integral over C, now we're just going to put a negative outside our integral, and we're going to say we're doing this integral over negative C. And so that puts us in the positive orientation. So that takes care of it. If our orientation is messed up, we can always fix that. So we take the integral over our, again, of course, this is our P value for a vector field, and then dx, this is going to be our derivative, dx, and then plus e to the y plus x squared dy, again, that's going to be our q times our dy. And in order to find the line integral, all we're going to do is we're just going to take, use Green's theorem, take the double integral, do the partial of q with respect to x, and then do the partial of y with respect, do the partial p with respect to y, and then we'll do the double integral. So we'll go ahead and substitute in, and we have, when we do the partial of q with respect to x, we're just going to get 2x minus 2y. We're just going to get 2x. When we do it for q, we're going to get, with respect to y, we're going to get 2y, and so we have 2x minus 2y. Now, we're doing this over a double integral. For x, we're going from negative pi over 2 to positive pi over 2, and for y, we're going from 0 all the way up to that function y equals cosine of x. So we're putting that in terms of x. So here's our double integral. And now we're just going to evaluate this double integral like we have been for the past 2 months. We're going to take the inside first. So the derivative of 2x minus 2y with respect to y is just going to be 2xy minus y squared along cosine of x to 0. Substitute in cosine x for y. We get 2x cosine of x minus cosine squared x. And when we plug in 0, that just wipes out. Now, we integrate again, but before we do so, again, change cosine squared to half, 1 plus cosine 2x, and then we can integrate this. Integrating 2x cosine x, that's going to be integration by parts, and so I here did the tic-tac-toe method. For that, to get 2x sine x plus 2 cosine x, when I integrate it, 1 minus 1 plus cosine 2x, that's minus 1/2 x plus 1/2 sine 2x. And then I hit back one too many times. Okay. All right, there we go. And then I'm just going to substitute into my integration pi over 2, negative pi over 2. When I do so, I'm left with just pi plus 0 minus 1/2 pi over 2 for the first, when substituting in pi over 2. Pi minus 1/2 minus pi over 2 when I substitute in negative pi over 2. Negative 1/2 times negative pi over 2. I get negative pi over 2 on the inside, but then I have that negative on the outside, so I just get positive pi over 2.